Hey math people, so let's talk applications of derivatives. I don't want to talk just basic find dy dx of this, that's just finding derivatives. What I want to do is I want to find the non-contextual application. So I'm talking tangent lines, normal lines, intervals of increasing, decreasing, concave up, concave down, relative extrema, which is what we're doing here, and absolute extrema. So mins and maxes. A little bit of EVT action is what we're going to use here. So let's get to it. We'll do related rates on another video. That's more contextual stuff. So I have a parabola, which means we have one absolute min or max, depending on the sign here. It's going to be an absolute min. However, we're on a closed interval. So since we're on a closed interval, you have to consider endpoints. What do we test? So what do we test for extrema with extreme value theorem? We're going to look for three things. So test to see when your derivative is equal to 0. So we're going to be doing that. Test to see when you have points of non-differentiability. So when is it ability? When do we not have a moment where we can discuss the derivative? So think about like an absolute value v. Right on that bottom, you can't find, that's non-differentiable at that bottom point. So with that said, you would look to see when you get something kind of strange, like a 0 in the denominator, for your derivative. And then the last point is the endpoints. You have to always consider the endpoints when it's on a closed interval, which we have. So if we are continuous, and maybe I'll do this in a different color here. If we are continuous, I'll put it for this one because it's a parabola. Continuous, and we are on a closed interval, we can therefore apply EVT, which says it guarantees me extrema. It'll guarantee me an absolute min and max within this interval. So let's get to it. My candidate, so I'm going to make a table for this. So I'll say x, f of x, so the output. Let's look for derivative to 0 first. So the derivative, y prime, of this expression is going to be just 2x minus 2. Setting this to 0 to find my potential min or max is quite straightforward. We just simply move this 2 on over to the left. You get an x value of 1. So on this parabola we have our vertex is going to be at an x value of 1. If we plug that into the expression, we can do that quickly. We get 1 squared minus 2 plus 1. Okay, so this ends up being 0, right? Back in math. So you get 0 for that guy. That is potentially a min or max, we'll see. And then you also have to consider points of non-differentiability. This is a line, and the domain of this line is all real numbers, so there's no points of non-differentiability. That's done. And then lastly, consider the endpoints. If we consider the endpoints, we actually lucked out. 1 was already one of them. So it just so happens that the x value of 1 is both a moment where your derivative is 0 and is an endpoint for this particular problem. It won't always be that case. All right, what else? The other endpoint is 3, so I have to consider that as well. Plugging in 3, that's a little annoying. Do that in blue over here or something like that. Plug it in 3, I get 3 squared minus 2 times 3 plus 1. Can I math? I don't know. So 4? Yeah. So these are my 2 points. And when you have just 2 points, one's going to be a min and one's going to be a max. So in this interval, and feel free to graph this on your own on Desmos and consider the interval from 1 to 3. It looks like we have a minimum on 1, 0 and a maximum on 3, 4. So parabolas are pretty simple. It's when you're dealing with very strange things with points of non-differentiability and blah, 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 and lots of different zeros for your derivative. That's when it gets a little bit more involved. So let's try another. So 2x squared plus 12x plus 19. And this is going to be from -4 to -2. Okay, so set the derivative. Well, first off, I guess we should see if EVT can be applied, similar to how we did in the last case. So this is in fact continuous. It's a parabola. It's continuous on all reals. And it is closed. So therefore, we can use extreme value theorem. That's all I'll put that. So therefore, we can use EVT. EVT is good to go. And it's just shorthand for that idea. All right, so let's first set the derivative to 0. So y prime here will be 4x plus 12 if we're taking that first derivative. Setting this to 0, let's see what we get. Okay, looks like we're going to get a slightly more interesting case here. Move the 12 on over, we get negative 12 is equal to 4x, so x is negative 3. And sure enough, that is within the interval. That's good, and it's actually inside of it. It's not on an endpoint, so we're going to have a few candidates to test through. So we're going to have x and f of x. Our first one will be an x value of negative 3. And oh man, I don't feel like plugging that in. Okay, so we get 2 times negative 3 squared plus 12 times negative 3 plus 19. Okay, this is 9. 2 times 9 is 18. Minus 36 plus 19. Negative 18. Okay, I think it's just 1, hopefully. Okay, so first candidate is negative 3 comma 1. Let's test the endpoints. So we're going to test negative 4 and negative 2 as well. The reason why I jumped right to endpoints is because there are no points of non-differentiability. The domain of the derivative is all real numbers. It's just a straight line, and it's nothing fancy is happening there. So let's just say you had like a derivative of, say, like y prime is equal to something over x, I'm not sure. So you would simply consider the x value. So long as it's defined on your initial curve, you would consider that as a candidate. Because like I said, if you observe a absolute value, right down here, that is a corner that's non-differentiable, and sure enough, it is actually your min. So that's the last piece of the puzzle. It didn't happen in any of these two because they're basic parabolas, but it can happen. So let's just plug in negative 4. So a little bit more hand math I got to do. So plugging in negative 4, and I'll just squeeze it in over here. 2 times negative 4 squared plus 12 times negative 4 plus 19. Okay. 16, 32. This is 48. And plus 19. 16. Negative 16 plus 19. You end up getting 3 for negative 4. Should get the same thing for negative 2, by the way. Let's see if we do. I'll just do the mental math on it. So put the math down here, I guess. 2 times negative 2 squared plus 12. And you're plugging back into the original, right? You're looking for extrema on the original, not in the derivative. We're not using the derivative for the endpoints. Right? Now that that's out of the way. So this is 4, this is going to be 8, this is negative 24, and this is 19. So negative 16 plus 19, okay, you get the same thing. That makes sense. It's a parabola, and you get symmetry on the sides. So if the negative 3 comma 1 is its vertex, then if you go 1 unit to the left and 1 unit to the right, it's a symmetrical shape. So these should be the same. That makes perfect sense. So what would we say here? We would say that this guy is our min, and together these two make up our absolute maxima. So the next one, we'll just call it number 3. Y is equal to quantity of 4x minus 20, and this is all to the 1/3 power. All right, I can already see where an issue is going to come into play, and this is from 2 onwards to infinity. All right, so first off, I cannot use EVT here. We are not guaranteed extrema in this problem. Reason being, this is not closed. so I cannot apply EVT. I can still hunt down my extrema, but I'm not necessarily guaranteed a min and max here. I might just have one, I might have none. It depends on the problem at hand. Alright, so let's start with the derivative though. So if I take the derivative, I end up getting 1/3 times 4x minus 20 to the, subtract off 1, negative 2/3. Okay, that's the same thing as 1 over, oh, not done yet. You mustn't forget the chain rule. Yeah, so you had to take the derivative of the inner expression. Derivative of 4x minus 20 is just 4, the 4 in front. Cleaning this up, we're going to keep the 4 up top. Let's bring this down below, and we're going to have a 3 down there too. So it'll be 3 times 4x minus 20, all to the 2/3 power. Alright, so if I set this to 0, are there any moments, is this a thing? How about that? Can this be 0, ever? Is there any x value that would warrant this thing becoming 0? No is the answer, because I have this 4 up top. I always have a 4 up top. It's never 0. So with that said, there are no points where I have a min or a max via a derivative. Okay, it doesn't switch from a positive slope to a negative slope at any point. Alright, so we're done with this guy. Points of non-differentiability, that sure does exist. So let me erase this for now. Points of non-differentiability, yeah, that happens. That happens when x is a problem. So x is down in the denominator. When is that going to be an issue? That's easy to find. So for what number would cause a 0 down below in the denominator? Looking like a 5 to me. If I were to plug in a 5 down here, 4 times 5 is 20. 20 minus 20 is 0. And yeah, sure, 0 to the 2/3 power is 0. I'm dividing by 0 here. So if I draw my candidate table, candidates, and just bear in mind that EVT is not applicable here. 5 would be the issue. That would be one number I'd consider testing. And if you plug 5 back into the original expression, you end up getting 0 from that anyway, right? This whole thing goes to 0. So that was an easy plug-in at least. Alright, checking the endpoints. Okay, so let's check the endpoints. We don't have an endpoint to the right, but we do have 2. So we can play around with 2. If I plug in a 2, let's see what shoots out. Okay, so plugging in a 2 there. Let's do this in a different color. So 4 times 2 minus 20 all to the 1/3. So it would be the cube root of that. This is an 8. 8 minus 20 is negative 12. So it's the cube root of negative 12. Okay. Cube root of negative 12. Alright, now remember these are candidates. Just like in the other problem, we kind of considered the general shape of it. I know the way that cube functions look. They look generally, so I'll just say x, cube root functions that is, looks like this. And there's some shifts applied to it. We're really not going to have any sort of max in a situation like this because I go on forever. It's going to take on this shape generally. It's a bit stretched out, and sure, there's a little bit of a shifting action there, but I go up forever. So since I go up forever, I'm not going to have an absolute maxima here. So I have no absolute maxima. This is always increasing. So with that said, no. We cannot, it's very tempting to label up this 5, 0 as a max, but since EVT did not apply, because this is not a closed interval, I was not guaranteed that, and sure enough, I don't even have it, because it goes up forever, that's infinite. Alright, what else? So I might have a min though. In fact, I do, because I'm cut off on the left side at some point, at 2. So recall that this is not the same graph as that. I will have a min. Since this is always increasing, I will have a minimum. And it's easy to see that this is always increasing because no matter what you put in for x here, it'll be a positive slope. Right, even if you put in a negative, because you're squaring it. with that said, which of the two are lower? Sure enough, this is my guide, this is my min. So I don't have a max in this case. Okay, looking at the next one, we are dealing with, so we'll call it number 4, like I said. We're dealing with y is equal to negative 5x plus 20, all to the 1/3. And this will be on the interval from -5 to -2. Non-inclusive on either end. And very quickly this becomes a problem that I really can't do much with. I have no endpoints to consider. When I take the derivative, I run into a similar situation that I was in before because it's a cubic root. I won't have any points where the derivative is 0. I'll only have 1 point of non-differentiability. And even then, that's not going to be helpful. The reason being, again, it has to do with x cubed, cube rooted. If I have the cube root of x, it looks generally like this. So the point of non-differentiability here, not helpful. It'll be a point where I have a vertical tangent. And that's usually not the helpful kind. The ones that aren't going to be helpful are when you have a cusp or a corner. Those will be a little bit helpful with mins and maxes, but not here. So let's run through all the ideas with this. First off, EVT can't even be applied, so I'm not guaranteed extrema. I have no points. You can find the derivative. In fact, I guess we can do it really fast right now. Y prime is going to be 1/3, and we'll keep the negative in front of the 1/3, times 5x plus 20, all to the -2/3, times 5. You cannot solve that for 0. That's never 0. And one last step of simplification will be obvious in showing that. I have a -5. I have a constant up in the numerator. So down below I have the 3 times 5x plus 20, all to the 2/3. So this is no good. Point of differentiability, yeah, sure, there's a point of non-differentiability. You can plug that in. It's going to be -4. But it's not going to help you. You're going to have a vertical tangent there, so no good. And no endpoints here. I don't have endpoints. It's tempting to say that they're endpoints, but remember, with open intervals like this, you get infinitely close to it, but you never quite approach it. So sure, you can say that at -4.99999, that might be pretty small or pretty big, who knows. But I can just tack on another 9, and then another 9, and then another 9. So I never quite actually establish and hit that point. So endpoints are out the door. You're not guaranteed any extrema for this problem. In fact, we just don't have any. All right, the next two problems aren't actually really derivative based, but the idea is going to be helpful at a point later on in the video for a mean value theorem. So let's just talk about the general idea of average rate of change, even though that's kind of a pre-calc topic, but it's still useful in calculus, early phases of calculus. So actually we'll juggle two problems at the same time. I don't think that's anything too crazy. So you want to find the slope, essentially. You want to find the slope from one input to the next within a closed interval. So average rate of change is what we're doing here. AROC, what it's called. There's a formula for it. It goes like this. F of B minus F of A all over B minus A. That's what I want to do here. Where A is your first input and B is your second. So we're looking for an average slope, right? These things are curvy things. They're not straight. We want to find an average rate of change within this interval. On average, how do you change from -1 to 0 or from 2 to 5 over 2? So we're going to do this. Denominator, so sometimes people say AROC is equal to average rate of change. Denominator is just going to be B minus A, so it's going to be 0 minus -1. And then numerator, you want to evaluate them. So I guess we can do that off to the side in green here. So if I want to evaluate, say -1, 2 times -1 squared plus 1, this is 3. And likewise, 2 times 0 plus 1, well, this is just going to be 1. So when I plug these in, this was my f of b, and this was my f of a. Finishing up the problem, this should be reminiscent of your Algebra 1 days. We end up getting -2 over 1. So the average rate of change here, the average slope of this parabola from -1 to 0 is -2. All right, let's look at the next one. Same story. Let's find that average rate of change, A rock. Let's do the denominator first, it's easier. My B is this guy, and my A is this one. So it's not obvious at this point. The interval is always provided as A comma B like that. So plugging in my A, I get 2. All right, so this is an easy expression to plug into. I guess I can still do it in green, but nothing too crazy. Plug the 2 in, that's just a half. And if I plug the 5/2 in, this is just saying the reciprocal of 5/2, which is 2/5. Flip that fraction. So we're going to have 2/5 minus a half. It's a complex fraction, looks a little scary, but nothing too bad. 2/5 minus a half, that is -3/10, right? Up top, because this is just 5 over 10, and this is 4 over 10. So that's not 3/10. That's something else. Try to do it mentally, but didn't pay off. Okay. Whoops. -1 over 10. All right, next one. Let's do this one over here, because clearly I can't do it in my head. 5 over 2 minus 4 over 2, that's just a half. Okay. So dividing by a half is the same thing as multiplying by 2. So we should get a final answer of -2/10, or a -5 here for an average rate of change. So let's take a break from that stuff, and let's just talk about finding tangent lines. So number 7. I'm going to give you a curve. I'm going to give you a negative cubic. So negative x cubed plus 2x squared. We're going to subtract off 3. And what I want to do is I want to find a tangent line specifically at 2, -3. So tangent lines, or just general, how about this? Take a step back. Lines in general. So I'm going to write line formula. There's a few of them, right? You should remember we got point slope, slope intercept, and standard form. My favorite is point slope. That is the perfect version of a line. And it goes a little like this. Y is equal to m times x minus x sub 1 plus y sub 1. You may have learned it with the y sub 1 on the left. Feel free to do it that way. I don't care. I like isolating the y. It looks nicer. So I got to find some things. I got to find the slope. I got to find my x sub 1 and my y sub 1. But not really on the last two, because those are both provided. Essentially, I'm just looking for the slope. And that's actually not too bad. I need to find the first derivative. Power rule time. So bring that 3 up front, subtract off 1. Bring that 2 up front, subtract off 1. And then lastly, a constant goes away. What I want to do now is I want to find the slope at this moment. So I want to evaluate this at 2. So we could do that. And this will tell me the slope at next value of 2. So this is 4. This comes out to -12. This is 8. -4 is my slope. That's my m value. This is my x sub 1 and this is my y sub 1. So let's just bring them all together. So you, and you. To form our tangent line, which is going to be y is equal to -4 times x minus 2 and then minus 3. It's another reason why I like having the y sub 1 on the right, is you don't have to keep in mind that it should have been a negative like you do with the x. So that is the tangent line of this curve at 2. So that's what is a tangent line? I guess we can really briefly graph this. Let's just say it looked a little like this. It's not going to look exactly like this, but it's, I don't know, close enough. On 2, -3, which we'll just say is arbitrarily right here, a tangent line is a line that just, so maybe I'll do that guy in blue. It just cuts it. It just pierces it. and it skims it for just one point, and then it never touches it ever again thereafter. So that's what we just did. The graph's probably not perfect, but you get the idea, hopefully. Feel free to graph both of these on Desmos, and you'll see, so this guy, and you'll see roughly that idea. So tangent lines are cool. They cross only once, and they borrow the same exact slope at that precise moment of the curve. There's another thing called a normal line, which is fancy words like orthogonal come to mind. Terrors from linear algebra, which one day you'll maybe take. But anyways, it just means perpendicular. And so instead of taking on the same slope, which is like parallel, you just go perpendicular. You just make your slope the negative reciprocal. And that's that. So this time around, we're dealing with y is equal to. So this is number 8. Again, that's like a meme. I don't know how to count. So we have y is equal to negative, I try though, negative x cubed plus 4x squared minus 4, and we're dealing with it at 0, comma, negative 4. Yeah, like, I don't know, maybe like a third of my worksheets aren't numbered properly. That's how it goes. Alright, let's find the slope. Yeah, let's find the slope at 0. Let's see what happens. First derivative time. We get y prime is equal to negative 3x squared plus 8x. Constant goes away. Okay. Let's evaluate this at 0. So we get negative 3 times 0 squared plus 8 times 0. Ooh, that's weird. Okay, no, don't panic just yet. But we do end up getting a slope of 0. And if we're talking about tangent line, this isn't too bad. It's actually, so I guess what I'll do is this for fun. The tangent line, so it's still going to use that same shell of a formula which I erased. We're still going to use y is equal to m times x minus x sub 1 plus y sub 1. We're still using this. Tangent line, if this is the slope, we're going to say y is equal to 0 times x minus 0 minus 4. So this is just a horizontal line, negative 4. That's all that is. So what is perpendicular to a horizontal line? A vertical line. The slope for something like this would be infinite. It would be undefined. So the perpendicular slope here would be undefined. If you're dealing with a line that has an undefined slope, that's written as x is equal to. So whatever the x value may be, in which case it's 0. So this one had some tricks up its sleeve. The normal line, instead of it being the horizontal line at the y component, it will be a vertical line, which is x is equal to, at the x component. X is equal to 0. Generally, how does this thing look? It looks, so I am cheating, it looks like this. So should make a little bit more sense now. This is going to be a bottom, like a little valley of our cubic curve. It's going to be right at this moment where it switches its increasing and decreasing. So it goes from decreasing to increasing here. It's a candidate for extrema, really. It's a local min in our case. And here would be our tangent line, here would be our normal line. First one here, so we're looking for all mins and maxes, both global and local. Negative x squared all over 2x minus 2. Alright, so I have no endpoints, so I don't have that to consider. Points of non-differentiability might exist. I'm not sure if that's going to help us too much. Let's look for the derivative first. That'll be most helpful. So y prime, oh man, a little bit of quotient rule action here, I guess. We'll attach the negative up top. That'll make our life a little bit easier. So let's get to this. So low d high. If you don't know how to find derivatives of quotients, we use the quotient rule. And I guess we can write it this way. So if we have y is equal to f over g, and these are functions of x. Y prime is going to be equal to g of x times f prime minus g prime times f all over bottom squared. That's quotient rule. And I want to apply that here. So let's do that. So our low is 2x minus 2. D high, we're going to get a negative 2x minus high d low. So we're going to get negative x squared. And derivative of the bottom is just 2. That's an easy simplification. A little bit of distribution there. Nothing too bad. And then lastly, this is going to be all over low squared, which looks like that. So let's do some math. Let's distribute this guy in and simplify this guy to the right. So we end up getting negative 4x squared plus 4x plus 2x squared. It's going to be all over, same denominator. Let's not touch it for now. All right. Up top we end up getting 4x minus 2x squared. And yeah, I don't really care about bottom. So let's think about bottom for a second. What would cause a point of non-differentiability? The number 1 would be bad for this because then we get 2 minus 2, which is 0, and then that goes away, and then that's no good. So 1 is a potential candidate here. So we'll do that. So create a little table. Something does happen at 1, you have a point of non-differentiability. But let's consider the initial function. So with our derivative, 1 is an issue, unquestionably. If I plug in a 1 down below, you get 0 down below. But the same thing happens over here. If I plug in a 1 in this expression, it doesn't exist. What's going on here? There's an asymptote on 1. So you do not consider that as a possible candidate. So we just established in this video that asymptotes and vertical tangents are not going to be too helpful in finding candidates for extrema. What is going to be helpful is cusps and corners. Those are going to be a little bit more helpful. So 1 is not a candidate because it doesn't exist on my initial function. Alright, so we got to figure out when this thing is equal to 0. So let's set it to 0, aka set the top just to 0, because that's how you get a number to be 0 when your numerator is 0. So 0 is equal to 4x minus 2x squared. Let's factor here. Let's factor out a negative 2x. Yeah, let's do that. Because over here we're going to end up getting a positive 1, or a positive x. And I'll put that up front now. And over here we're going to end up getting a negative 2. Yeah, if I divide out a negative 2x from this, you get negative 2. Alright, so set these both to 0. And you end up getting x is equal to 0 and x is equal to 2. Those are my candidates for extrema. The point of non-differentiability didn't help us, and we have no endpoints to test, so these are really it. Plugging in 0, I get 0. Plugging in 2, dang it, I gotta do work. So I'll do that, I guess, in green. This will be negative 2 squared over 2 times 2 minus 2. So this comes out to negative 4, and then down below I end up getting 2, so negative 2. So where are my extrema? Well, you're looking at them. They're right here. With this said, this is going to be your min, and this is going to be your max. All right, we're dealing with negative 5x minus 30, all to the 2/3 power. And again, we're looking for relative extrema of this thing. So let's do it. Okay. Let's consider not the endpoints, because that's not something we have in a situation like this. Y prime is probably the direction I'd start. So taking that first derivative, you get negative 2/3. Quantity of 5x minus 30, all to the 1/3. And then we're multiplying by, or all to the negative 1/3, right? Because if we're subtracting off 1 from 2/3, 2/3 minus 1 is negative 1/3. So that's negative 1/3. And don't forget the chain rule, derivative of inner is just 5. So, cleaning this up, we get a negative 10 up top, right? 2 times 5 is 10. And then down below we have a negative exponent, so we're going to bring this expression down there. And it's the cube root of it, so bear that in mind. And then we can't forget this 3. So when is this thing ever 0? Never, because our numerator is 10. So I can't do the same thing I did in the last problem. So, oh darn, that doesn't work in our favor. Maybe points of non-differentiability might help. That could be a direction to go in. So when is the denominator going to be an issue? So you would set bottom to 0. More specifically, how about we just set this component to 0? Because if this is 0, then the 0 to the 1/3 is 0, and 3 times 0 is 0. So just setting this guy to 0. Some quick mental math, because you're calc students and you know how to solve two-step equations mentally like this. You end up getting 6. So an x value of 6 is the only candidate I really have to play around with. So one last time, let's recap. No endpoints to test. Never is this derivative ever 0. And then lastly, there's only 1 point of non-differentiability. So what do I do in a situation like this, where I have nothing to compare it to? I just have a lone candidate, right? If I take this 6 and I plug it in, sure enough, it exists. This is going to be a relative extrema. It's going to be a min or a max. If I plug this 6 in to our expression here, this is 0. 0 to the 2/3 is 0. So this is my guy. It's 6, 0. Is this a min or a max? How do I know if it's a min or a max? It's not too crazy. You just test numbers nearby. This is going to be then, therefore, a maximum. Man, I should probably know these graphs by heart by now, but doesn't this create a cusp? I'm going to cheat, and I'm going to see if this creates a cusp. Heck yeah, this creates a cusp. If you do graph this expression, it looks roughly like roughly like this. There we go. So 6 zeros right here, and that's my max. So hey, look at that. What I said earlier stands correct. Points of non-differentiability. What are you looking for with relative extrema? Cusps and corners. Vertical tangents and asymptotes, not so much. So next on the agenda, intervals of increasing and decreasing. What we want to do is we want to find the critical points. So how do we establish critical points? Points of non-differentiability and well, when your derivative is set equal to 0. That's the easy part. Let's do that one first. Maybe not so easy when you have to use quotient rule, but easy part, the part people remember. So low d high. Low is this guy. D high is this one, negative 2x. So low d high minus high d low. So we got negative x squared, and then d low is going to be just 4. Low d high minus high d low. Okay, that works. All over denominator of 4x minus 4 all to the second power. Actually, let's keep going with this. So let's set this to 0 after we simplify it. So distribute that guy in. We end up getting negative 8x squared plus a number 8x. Okay. And then at the very end here, we are going to add 4x squared. All right, and then down in the denominator, I don't feel like touching that. I won't do that until I have to, and maybe we can get away with not. All right, up top in the numerator, one last step to simplify. We end up getting negative 4x squared plus 8x. All right, so points. Where our derivative is 0, I just set top to 0. And that's exactly what I'm going to do here. I'm going to say negative 4x squared plus 8x is equal to 0. This is a simple quadratic. No need for the formula when we know how to factor. We can pluck out a 4x, making a normal x on the inside minus 2. So setting these to 0, we end up getting an x value of 0 and an x value of 2. These are my critical points when I potentially switch signs. I have to test for them on a number line thereafter. All right, points of non-differentiability. They do occur, actually. So what would cause an issue down in this denominator? Well, the number 1 would certainly cause an issue. So we do have to consider that. We're not looking for extrema here. We're looking for signs. So we don't exist on 1. Let's be clear here. The asymptote is on 1. If I try to plug 1 into this expression, that would be a problem because I'm dividing by 0. So this is not an extrema. It is simply a critical point, though, where I have to consider a sign change. So let's do that. Let's draw a number line. So we'll say point of non-differentiability. This is going to be at an x value of 1. If you set this expression to 0, move the 4 over, divide by 4, you get 1. That's a bad guy here. So let's off to the side. Yeah, I can write over here. Draw a number line. So this will be for f prime. And I have my candidates, 1, 0, and 2. Or a more conventional way of saying it is 0, 1, 2. I need to consider the signs now on both ends of this. So let's do precisely that. The way we're going to approach this is plug in values. If I plugged in a -1 to this expression, the derivative, not the initial, I don't care about that anymore. I care about when we're increasing and when we're decreasing. If I were to plug in a -1, because that's to the left of 0, what shoots out? We're looking at just the numerator here, because the denominator, well, it's squaring it, it's going to be positive. I'm looking for the sign. And I guess I can show some of my work. Yeah, I can do that. I'll do that over here. So sine of f prime work. So we're going to type in, so I wrote f there, and I'm using, here, we'll stay consistent. We'll do y prime, and I'll write this as y prime, just for the sake of consistency. There we go. All right, so y prime of -1. If I plug in a -1 here, I care about the sign. I don't care about what the number is. I care about if it's positive or negative. So down in this denominator, I get a positive number. Over here, it's just going to be a +4. And if I plug in a -1 here, it turns out to be a +4. But I have this negative in front, so it'd be -4. And then over here, I'd have -8. So -4 minus a -8. This is going to be a negative number. Okay, so let's actually move to the right of 0 now. I unfortunately can't choose 1, because if I try to choose 1, I get a 0 in the denominator. I need to choose something in between 0 and 1. So I'm going to choose, like, say, half. If I were to plug in a -1/2 here, this is positive, this will be positive, this will be negative, but it won't be quite as big as this. So actually this is going to be positive. Let's plug in a point in between 1 and 2 now. So I'll plug in 3/2. Alright, so if I plug in 3/2, this is positive, this will be positive. This will also, no, this is going to be negative, right? And I actually do have to test to see which one wins this battle. I'm going to plug in 3/2 to this, and I'm going to plug in 3/2 to this, and I'm going to see what happens. So for the numerator, it'll be -4 times 3/2 squared plus 8 times 3/2. So what's going to win? Which one's going to be bigger? That's going to tell us what sign we are. And then the denominator is going to be positive, so I'm not too concerned about that, so it'll be over positive. All right, up top I end up getting 24 over 2, which is 12, and then I'm subtracting off, this is 4 times 9 over 4, so it'll be just 9. This is going to end up being positive. So I don't know if that's cut off on the side of the screen there, but y of 3/2 is a positive number. You end up getting 3 up in the numerator for that, and a positive number down below. Lastly, let's plug in a number to the right of 2. So I'll say y of 3 is tempting to plug in, but is it easier just to plug in a super big number? I'm just going to say y big. You can choose anything to the right. So what I'm doing right now is I'm testing, I'm plugging in values to the right and left of 0, 1, and 2. Those are my critical points. I'm plugging them into y prime, and that's going to give me my slope at those points. So the slope at -1 is negative, because I got a negative number when I plugged it in here. The slope at a half is positive, because I got a positive number when I plugged it in here. So on and so forth. So when I plug in 2, which is, or a number bigger than 2, let's plug in 1,000,000, for example. Is 8,000,000 going to be able to take out a negative 4,000,000,000,000? The answer is no, that's going to be negative. So looking at my first derivative chart here, it goes negative, positive, positive, negative. Negative, positive, positive, negative. So let's write down our final answer in interval notation. So this problem was very involved. So increasing when was it increasing? So from 0 to 1, and I'm going to stop on 1 because I know that 1 is an asymptote on this. The number 1 came into play because it was a point where it was non-differentiable because it didn't exist at 1 at all. So I'm actually hopping over this 1. And then I'm going to resume from 1 to 2, closing that interval of increase. And then for decreasing, it looks like we were from -infinity to 0, and then union 2 to infinity. Okay, looking at number 12, we have y is equal to -4x minus 8 all to the 2/3 power. Let's start by addressing the cusp in the room. That's 2/3, that's going to create a cusp based on the last problem we did a few problems ago, not the last one, but a few problems ago, we graphed it and we got 2/3 creating a cusp. So we will have to consider that. Anyway, y is equal to -2/3 times 4x minus 8 all to the -1/3. Chain ruling this to get a 4 for the derivative of the inner expression. Let's clean this up. So that was y prime, sorry. If we clean this up, we end up getting a -8 up top. Down below, we keep that 3. And then this is a negative power, so we're going to bring this down to the denominator. We get 4x minus 8 to the 1/3. So when is this thing ever 0? For the third time, I think. Never. If I set this to 0, it's not ever going to be true because I have a constant up top, and that can't be 0. So really all I have to consider as a critical point is points of non-differentiability. So that's setting that bottom to 0, actually. And again, more specifically, the 4x minus 8 part. So I guess I can show my work here. I'm kind of choosing when I want to show and when I don't. So I have 4x is equal to 8. Looks like I'm getting a potential point where I switch my sign at x is equal to 2. But we have to test it around it first to see if that's the case. So I'm going to draw my y prime line. And 2 is going to be the only lone number on here, as opposed to the last problem, which had 3. And first off, we should clarify, is something special happening on 2? If I plug it in, yeah, you get 0, so it looks like I'm going to be at an output of 0 there. Okay, let's test some points around it. So let's plug in 0 to this thing. And let's plug in, I don't know, maybe 10 to this thing to see what happens. And again, I'm only looking for the sign. So signs for f prime. I'm going to do this off to the side again. So I'm going to look for y prime of 0. So it's going to be positive or negative. If I were to plug in 0 here, okay, I get -8 to the 1/3 power. That's -2. So -8 over -2 is 4. 4 over 3, that's positive. Okay. What about y prime of, say, 10? I like 10 because I know that that's big enough for me to see that this is going to be a big positive number here, and the cube root of a big positive is just positive. So it'd be negative 8 over positive. So that's going to be a negative number. Okay, so I'm positive over here, and I'm negative over here. And on 2 I do exist. So I wanted to check maybe like 30 seconds back whether I existed on 2. If you think about the problem we just did, we were non-differentiable on that asymptote, sure, but we also didn't exist on that asymptote, so I couldn't include it within the intervals. Here, 2, sure, it's non-differentiable at 2, it's a cusp, but it exists. That's the point I'm trying to connect here. You can plug in 2. It's okay to plug in 2 here. You can take the 2/3 power of 0. That's fine. So in which case, I'm including that in my intervals. So when I'm increasing, I will be increasing from negative infinity, we never include the infinities, by the way, up to 2, and then decreasing from 2 to infinity. All right, y is equal to x squared minus, I don't know what number we're on at this point, 13 I think? Sure, we'll just call it 13. X squared minus 8x plus 15. If you know anything about concavity in this shape, you should already know the answer. So for concavity, we have to take the second derivative. Y prime is 2x minus 8, and y double prime, that's just going to be, well, 2. So when you have an always, the way we test for concavity is to take the second derivative and to tell when it's positive and when it's negative. When you have just the number 2, when is the number 2 positive and when is the number 2 negative? It's positive forever, so it's concaving up forever. This is a parabola. It's an upward pointing parabola. It's always concave up. So with that said, we are concave up forever, and the way we say forever is that way. So concave down, we'll just say never for that. So 14 we can do with literally no work. Y is equal to negative 2x squared minus 16x minus 31. Second derivative of that, I'd be happy if you were able to just jump straight to the second derivative for this. Should be negative 4. That's always negative, which would suggest this will concave down forever. So concave up, never. Concave down, forever. Number 14. Okay, so it's going to be a cube. X cubed minus 3x squared plus 1. Y prime, so we want to take that second derivative. Y prime will be 3x squared minus 6x, and this goes away. And then y double prime will be 6x minus 6. So let's find those critical points for this time concavity. Looking for when it's equal to 0. This isn't too bad. You just set this to 0. You end up getting 1. And points of non-differentiability don't exist. This thing's always differentiable. It's a cubic and then a quadratic and a linear. These are always true for all real numbers. So we like the polynomial cases. Polynomial cases aren't too bad. We switch signs on 1. So if and now we're looking at y double prime, mind you, so we're plugging back into this guy. If I plugged in 0, which is nearby, and I don't have to do any side scrap work for this because it's just a line. If I plug in 0, negative 6 shoots out, so that's negative. And if I plug in, say, a million, because that's to the right of 1, 6 million minus 6 is a positive number, whatever that is, 5 million blah. So concavity here, not too bad. We concave up from 1 to infinity, and we concave down from negative infinity to 1. Okay, 2 more. I don't know if I numbered these properly. Also, My battery's screaming at me that it's going to die, so I got like 2 minutes, maybe 3. Let's do this quickly. I mentioned that average rate of change was going to be necessary moving forward, and that's precisely what we're going to do, but we're going to do it through the lens of mean value theorem. Mean value theorem states if you take the average rate of change on a closed continuous interval that's also differentiable on the open, then at some point in this interval, you must take on that slope. So that's what we're hunting down. So let's find the average rate of change first. We're just going to deal with 16 for now. So our AROC here, as a reminder, is f of b minus f of a over b minus a. So our a here is negative 3, and our b here is 0. Plugging in 0 is the easiest because this goes away, and we get a 2 for the first value. Plugging in a negative 3 is also not too bad. Reason being is that this is going to be a positive 27, and this is going to be a negative 27. They both go away. You're left with just this constant of 2. 2 minus 2 is 0, and sure enough, this average rate of change is actually 0 from negative 3 to 0. What we're going to do with that is we're going to set it equal to the derivative. So let's find the derivative first. Y prime is negative 3x squared minus 6x, and the constant goes away. We're going to take this 0, and we're going to set it equal to the derivative. It's a coincidence here that it happens to be 0, but whatever the number is, that's what you're setting it equal to and solving for. So here, this is not too bad of a solve if you can factor out a 3x, and on the inside you're left with an x minus 2. So there are actually 2 moments where this occurs. It occurs at 0, and it occurs at 2. However, we are not, one of these is not within this interval, the 2. We are ignoring. No, I take that back. So when I plucked out a negative 3, this should have been a positive, right? So with that said, a negative 2 is the one I want to consider. That's the only one, because this 0 is on an endpoint, and the endpoints are not to be considered in a scenario like this. So the only moment in which this happens, it's got to be inside the interval, and it's at an x value of negative 2. So what does this mean? The average rate of change is the slope at precisely x is equal to negative 2 for this provided interval. Same story can be applied over here. Average rate of change, still the same formula, so I'm not going to rewrite it. It's an easy denominator to find. That's going to be 2 minus negative 1. And then up top, let's plug in 2. We get 8 minus 4, which is 4. And 4 minus 3 is 1. Here we get negative 1 minus 1 to get negative 2. And then negative 2 minus 3 is negative 5. Okay, so this comes out to 6 over 3, which is 2. So let's take that y prime, which is 3x squared minus 2x, and this goes poof. We don't, right? Derivative of a constant's nothing. So same story over here. We're going to set this derivative equal to 2. We're going to find the x value moments where the average rate of change is the same as the slope instantaneously within this interval. So I taking a look at this, I'm feeling like we have to move this 2 over and unfortunately do some quadratic formula. So hopefully you remember your negative b plus or minus jazz. So we're going to get 2 solutions here, and maybe one of them's outside the interval, maybe they're both inside the interval. We'll see together. My b value is negative 2, so negative 2 is just 2. 2 plus or minus b squared minus 4ac. So that's going to be 4 minus 4ac. So it's going to be 4 times 3 times negative 2. This is all going to be over 2a. So, conclusion. As far as the solutions for this go, it's going to be 2 plus or minus 12, 24, 28, positive 28, yeah, over 6. And hey, this could be simplified, I think. Yeah, and you can break this into a thing, right? Root 28. You can break this into square root of 7 and square root of 4. Reason why this helps you, we know the square root of 4 is 2. So that's 2 root 7. Okay, not too bad. So this is just 2 root 7, and it's all over 6. Let's simplify it one step further. Divide everything out by 2. So we're going to end up getting 1 plus or minus root 7 over 3. Last thing to consider, are these within this interval? I believe they are. My calculator, or not my calculator battery, my brain battery is dying, as you can see, and my camera battery, I'm pointing at it, is dying out. I believe these are within this interval. You should check though for me. Yeah, because this is pretty much, let's just treat it like 3. So 1 plus 3 is 4, 4 over 3, that's inside of that interval. And 1 minus 3 is negative 2/3. Yeah, that's also within this interval. Both of these are in there. This is pretty much 3, right? Root 7, pretty much 3, 2 point something. With that said, there are 2 moments for this particular case in which the average rate of change is the same. So average rate of change being 2 from negative 2 to 2 is the same as the slope at the given x values of 1 plus root 7 over 3 and 1 minus root 7 over 3. Concluding our review of applications of derivatives. This took me a long time. I have a bit of a headache. I'm going to ask you to continue to math on, and I hope you do the same. I'll see you in the next video.